Okay, hey, grade 11 chemistry. This is our last lesson of Unit 3, and we're talking about empirical formulae or empirical formulas. And empirical means arrived at through experiment. So to explain what an empirical formula is, we saw in the previous lesson that glucose has a composition of this 40% carbon, 6.7% hydrogen, 53.3% oxygen. Let's do the same thing for formaldehyde. Let's get a percent composition by mass of formaldehyde. So we're going to go over here. Formaldehyde, if we look at it, 1 carbon, 1 oxygen, 2 hydrogens. So formaldehyde looks like this. Carbon, 2 hydrogens like this. So we could write that as SCH3U, for example. So that is 1 carbon, 2 hydrogens, 1 oxygen. And I'm not going to bore you with the details, but that is 12.01 grams per mole on my periodic table. This is 2.02 because there's 2 hydrogens, so 1 carbon, 2 hydrogens, 1 oxygen, grams per mole, and 1 oxygen is 16.00 grams per mole. When I add that together, I get some number. 12 plus 2 plus 16 is 14 plus 16, that's 30. 30.03 grams per mole. 30.03 grams per mole. And then to figure out the percent carbon is going to be 12.01 divided by 30.03. That's in grams per mole, of course. Gives us, let's see, 12.01 divided by 30.03. 39.99%. 999. No, 99. Yeah, okay. Percent H is going to be 2.02 grams per mole over 30.03 grams per mole. That's carbon. 2.02 divided by 30.03. 6.7 H, 6.73% H. My percent oxygen is going to be 16.00 grams per mole over 30.03 grams per mole, and that gives me 16 divided by 53.3. 53.28. Oxygen, 53.28% oxygen. When we look at those numbers, 39.9, 6.8, and 53.3, they're the same numbers, right? Which shouldn't be surprising because the glucose was C6H12O6. It's got the same atoms in the same proportions, and so in terms of percent mass, you'll have the same percent mass for the carbon versus the total, hydrogen versus the total, and oxygen versus the total. So this is where empirical formula comes in. Empirical formula, right? The empirical formula of the two of them are the same because they were arrived at through mass experiments, right? These through experiment. If we do the mass ratio, we find that glucose and formaldehyde have exactly the same mass ratios. And that's where the empirical formula comes in. It's the simplest ratio of atoms in a formula. But they have different, what we call molecular formulas, which is the actual number of atoms in the compound. Right? Formaldehyde looks like this. Glucose looks like this. Right, there's a lot more hydrogens and carbons going on. Right, there's glucose, but the ratios are the same. So different molecular formulas, the same empirical formula. Simplest ratio. So here's an example for hydrogen peroxide. The chemical formula of hydrogen peroxide is H2O2 because there's 2 oxygens and 2 hydrogens. But the empirical formula, if we were to do a mass determination of it, we'd find that we see exactly 1 hydrogen for every 1 oxygen. So we can, if we were just looking at the masses of the elements themselves, we could only be sure that we have 1 hydrogen for every 1 oxygen. We don't know that it's 2 and 2 in the molecule. So that's the difference between the chemical formula, or the molecular formula, and the empirical formula. So that's how that works. Other examples, any alkene, so propane, butene, pentene, all of these, they all have empirical formula CH2. So that's another example of that. So these are all different because they have different lengths in their chain, but they have the same empirical formula. It's always CH2. If you did a mass analysis on this one or on this one, you'd always see twice the number of hydrogens to the number of carbons. And so that's why we have to talk about empirical formulas. You wouldn't know which one you had unless you did more studies on it. So yeah, so empirical, arrived at through experimentation. We get empirical formulas from mass percent, and that's how we actually get empirical formulas, is looking at mass percentages. If you have the real mass of the compound, which you can get from something called mass spectroscopy, you can then figure out the true ratio. So you'd have, if you did it for this, you'd end up with this as the empirical formula. That is the empirical formula. But then you can find that the actual mass of the compound is 180. And when we did it, this was 30. So 180, if you found that the real mass was 180, you'd know that you have to multiply every single thing by 6, and you have C6H12O6, that kind of thing. So that's how that works. Now there's a way to go through this, and I'm going to show you how to do it. That's our next step, is just some example problems. So that's what we're going to get to. I'll get that set up. So here's a question. It's from textbook Nelson Chemistry 11, page 290, in case you're wondering. We get given find the empirical formula with percent composition of 35.4% sodium and everything else is nitrogen. So we know that the percent of sodium is 35.4% by mass, and the remainder is nitrogen. Let's write that out, right? We have 35.4% sodium, and we have whatever the remainder of that is, which would be what, 64.6% nitrogen. Right? I think that adds up to 100. Yeah, it does. Now the trick here is it's by mass. Right, by mass. So we can choose what our total is. And since these percentages add up to 100%, why not just make it, 100 grams? Why not just make it 100 grams? If we make it 100 grams, then we have 35.4 grams of sodium, and we have 64.6 grams of nitrogen. Right? We've just taken the percentages and turned them directly into masses. That's our first step. I'll explain why that's our first step in a second. The reason for this is, remember our great rule of stoichiometry. We cannot compare two atoms. We cannot compare two elements. We cannot compare two compounds unless we are working in moles. And so that's why I put it into grams, because I have a way to go from grams to moles. It's my periodic table. That gives me all of my conversion factors to go from grams to moles. So let's turn these into moles. And I turn them into moles by, and I can, I proved I do this by per gram, right? Per gram, because I want to cancel my grams. So my grams go on the bottom and my moles go on the top. It's 22.99 grams per mole, and this one is 14.0. What is it, 01? Yeah, 14.01 grams per mole. And that gives me some amount of moles. 35.4 divided by 22.9 is 1.55 moles of sodium in my compound, in my 100 grams of compound, my fake 100 grams, but it works. We can choose whatever mass we want. And 64.6 divided by my 14.01 gives me 4.61 moles of 4.61 moles of nitrogen. And so the question becomes, how are these related to each other? Well, it looks like it's about 3 times. It looks like it might be 3 times. So let's maybe take a look at that. All right. What happens if I multiply this times 3? If I have 3 sodiums, like I'm thinking maybe it's Na3N, right? Maybe it's what's that? So if I multiply that times 3, 1.55 times 3, 1.55 times 3 is 4.65, right? And that's pretty close. 4.65, 4.61, close enough. It's within 5%. So that's probably what the formula is. So we say then the formula is Na3N. But there is an easier way to do this. There's a much, much easier way to do this instead of trying to guess what the number we're multiplying by is. And that much easier way, and this is like the trick, is to divide everything by the smallest number. We divide that by 1.55, divide this by 1.55. Remember, we get to choose the masses here. We can choose whatever we want. And I'm just going to put my light on here so you can see it a bit better. There we go. Oh, that's really bright on me. That's okay. We choose whatever mass we want. So we divide them both by 1.55, which we're allowed to do. That's just going to be one sodium. And the 4.61 divided by 1.55 is 2.97. 2.97 nitrogen. So, sorry, I got that backwards. Sorry, it wouldn't be Na3N, it would be NaN3 because there's 3 times more nitrogen than there is sodium. My bad. So yeah, one mole of nitrogen to 3 moles of 1 mole of sodium to 3 moles of nitrogen. So then we suggest then that it is Na1 N 2.97. But that's not how formulas work, right? They have to be the single numbers, so it'd be probably NaN3, which is a real compound. This is azide. It's a polyatomic made out of nitrogen, which is kind of an interesting polyatomic. But that's what we say is our empirical formula, NaN3, and that's what, that's how they got it here too, right? They get that simplest ratio, and down they go. So I'm going to pause, and we'll set up the next problem. All right, let's do this one. It's a little bit more complicated. It says we have 69.9% iron and 30.1% oxygen. So 69.9% iron and 30.1% oxygen. That's our that's our 2 things. We're going to do that trick where we turn it directly into grams. 69.9 grams of iron and 30.1 grams of oxygen. And then we're going to turn it into masses. I don't think I need to prove it. We just divide by the molar mass here of iron and of oxygen. So I'm going to pull up my table. Iron 55.85 grams per mole. You can prove that the grams are going to cancel because we're grams and we're dividing by grams. And oxygen 16.00 grams per mole. And that'll give me some number of moles. Let's check that out. 69.9 divided by 55.85. 1.25 moles of iron. And my 30.1 divided by 16, 1.88 moles of oxygen, of iron and oxygen. Now the next step is that really important step. We take our 1.25 moles of iron and our 1.88, oh, I should make some room, 1.88 moles of oxygen. Now we're going to divide it by the smallest number. We want to find that ratio. Right? So we're divided by 1.25. Divide this by 1.25, right? So we're dividing by the same ratio. Just like in math, if we do the same thing to both things, we keep the same ratio going. So that's 1 iron. 1.8 divided by 1.25 is 1.504 oxygens, which is interesting, right? This suggests to me that my empirical formula has 1 iron and 1.5 oxygens. So it's like Fe1O 1.5, well, 1.504, I guess. So our job is to figure out what that could possibly mean as an empirical formula, because you can't have 1.5 underneath an oxygen. You can't have half an atom of oxygen. That's what this is suggesting. What we're doing is we'll just multiply everything by 2, right? 1.5 times 2 is 3. So it would be Fe2O3. That would be my empirical formula. And that's what's suggested as the empirical formula. Yeah, let's do a few more. Maybe we'll do 2 more and I'll finish the video there. Yeah, let's try out this second one, number B, right? B says we've got 18.4% carbon and 21.5% nitrogen. And the rest is potassium. Well, whatever 100 minus those is, right? 100 minus 18.4 and 21.5, 60.1% K, potassium. So we're going to do that trick. We're just going to change all these to grams. I'm just going to, it's grams. And then we have to figure out the number of moles. We're dividing by the molar mass. Carbon is 12.01. Nitrogen is 14.01. Potassium, I'll need my table for 39.1. 39.10 grams per mole. We'll get how many grams there are. So 18.4 divided by 12.01, 1.53 moles of carbon. We'll do 21.5 divided by 14.01, 1.53 moles of nitrogen, and 60.1 divide by 39.1. Oh, look, it's 1.54 moles of potassium. So they're all basically the same. I don't think we need to do the whole divide by 1.53 thing. We are just going to call it, it's KCN. KCN. I wrote the K first because it's the most positive thing. This is potassium cyanide. It's, just CN is a polyatomic, so it kind of makes sense that it might be that. But yeah, 1 to 1 to 1, right? Really, this is kind of, my masses are telling me it's K 1.53, N 1.53, and C 1.53. I guess K is 1.54. But it's pretty much just K1, C1, N1. So we assume that that's what it is. Any little description, any discrepancies are going to be based on experimental error. Okay, what's another one? Let's do let's finish this up. Let's do that aluminum one, and then we'll do that that carbon one. That carbon one looks pretty funky, so let's do this aluminum one before we get there. So we have 52.9% aluminum, and the rest of it is oxygen, which mental math is 47.1% oxygen. Change that to grams. and we'll divide it by their molar masses. What's aluminum's molar mass? I know oxygen, I don't know aluminum. Aluminum, 26.98. 26.98 grams per mole. And oxygen is 16.00 grams per mole. So we'll figure out what that is in terms of mass. 40.9 divided by 26.98 is 1.96 mole of aluminum. And the oxygen is 47.1 divided by 16, 2.94 moles of oxygen. Now here we have a pretty good whole number ratio. I don't think we need to do that trick to divide again. It looks like it's aluminum 1.96, oxygen 2.94, and simplest ratio, you know, that's pretty close to 2, and that's pretty close to 3. Like, really, really close. So let's call it aluminum 2, oxygen 3, and that'll be our empirical formula. All right, let's get to that last one, and it'll be the last one that we do. It'll be the end of the video and the end of the unit. Man, what a quick end to the unit. So 50.84, I'm just going to go grams because they give us all of it. So 50.85 grams, so remember that trick, percent to grams, 8.47 grams. So that's carbon, that's hydrogen, and that is oxygen, 40.68 grams of oxygen. We are going to divide it by, divide that by the molar masses of each of these. So carbon is 12.01, that's what it says on my periodic table. Hydrogen is 1.01, that's what it says on my table. And oxygen is 16.00, that's what it says on my table. I'll get my moles. I'm going to change color for my moles. I'm just going to swap over for, so 50.85 divided by 12.01 is 4.32, 4.23 moles of carbon. 8.47 divided by 1.01 is 8.38 moles of hydrogen. Well, 3.9, I guess. It's closer to 3.9 than 3.8. And 40.68 divided by 16, 2.54 moles of oxygen. So this is not, these are not great round numbers. These are not good. We can't like make a quick determination of what this this thing's empirical formula is going to be. So what we're going to do is divide by the smallest number. The smallest number here is the 2.54. So 2.54 is what we're dividing by. Divide this by 2.54 and divide this by 2.54. Once again, we have to do the same thing to each one, or else we're going to lose our ratio. We're going to lose our mole ratio. So we have to do the same thing. 2.54, 2.54, 2.54. And that's going to give us some numbers. I'm going to go back to blue for this because it shows up better under the light. So 4.23, okay, well, I mean, this one's obviously just 1. Right, this is just 1 oxygen. 4.23 divided by 2.54 is 1.66 carbon, and 8.39 divided by 2.54 is 3.30 hydrogen. So that suggests that it's, it's C 1.66 H 3.3001, and you got to think about what are you going to multiply it by to make it a nice round number. Looks like 3 will work because I know that 0.66 is about 2/3 and 0.3 is about 1/3. So if I multiply everything by 3, right? All of them by 3. I end up with 1.66 times 3 is carbon 4.98, hydrogen 3.30 times 3, 9.9, and oxygen 3. And that's pretty close, right? 5, 10, and 3, so C5H10O3 is what we suggest as our empirical formula. So that's how all of these problems work. We're going to do a bunch of them in class, as always. Yeah, that's how you find an empirical formula from a percent composition, and it's the last piece of the unit. So yeah, I'll see you guys in class, and there will definitely be a problem like this on the test. Yeah, bye.